Normal distribution, the central limit theorem for means and proportions. Let's first talk about the central limit theorem for means. So the central limit theorem for means. Suppose that the random variable x has a distribution which may or may not be normal. It has a mean mu and a standard deviation sigma. Simple random samples of all the same size n are selected. Then the following is true. The distribution of sample means, x bar, will, as the sample size increases, approach a normal distribution. The mean of all the sample means is the same as the population mean. The standard deviation of all the sample means is given by sigma, the population standard deviation, divided by the square root of n, the square root of the sample sizes. So here's the notation that we're going to use. The mean of the population is just mu on the right. The mean of the sample mean is mu sub x bar, is how we say that. It's the mean of the sample means. The standard deviation of the sample means, we use the notation sigma sub x bar. That's different than just the regular standard deviation. We have to adjust by dividing it, this population standard deviation, by the square root of n. So when you see those little subscripts x bar, it means we're talking about sample means. Okay, a couple of practical rules to follow. If the original population is not normally distributed, then for your sample size bigger than 30, the distribution of the sample means will be approximately normal itself. And as n gets bigger, the distribution of the sample means gets even closer to being normally distributed. If the original population is normal, then for any sample size, the distribution of the sample means is going to be also normal. Okay, let's do an example. Let's say that IQ scores are normally distributed, good, with a mean of 100 and a standard deviation of 15. Find the probability of randomly choosing a person with an IQ score of at least 133. Okay, a couple of things here. One to notice is at least. If they have an IQ score of at least 133, that means that their IQ score is 133 or bigger. So the first thing that we want to do is find the z-score, like we did in the last section. Unfortunately, it's not standard normal distribution, so our mean is not 0 and our standard deviation is not 1. So we're going to go back to using our formula z is x minus mu over sigma, and we would get 133 minus the mean, minus 100 over 15, to get a z-score of 2.2. And then going to our table, our standard normal distribution table, and finding the probability, remember that gives us the probability to the left of that z-score is 0.9861. So that's the probability that a person has an IQ score lower than a 133. So we want to find the probability of choosing a person of an IQ with an IQ score of at least or greater than or equal to 133. So that would be 1 minus 0.9861. And we have the probability would be 0.0139. Okay. That example was really similar to the examples we were doing in the last section. So let's change it up so you can see what the central limit theorem says. Let's say now that only 9 people are randomly selected. Find the probability that their mean IQ score is at least 133. So the big difference is we're only choosing 9 people, not the entire population. So we have to use the adjusted formulas for the sample mean and the sample standard deviation. Now, fortunately, the sample mean, remember, is the same as the population mean. So we're going to use 100 in the numerator for both. But the sample standard deviation, we have to divide by the square root of n. So here we'll get 133 minus 100, just like in the previous. And we, in the denominator, because we have a small sample, 15 divided by the square root of 9. And when we perform these calculations, we get 33 over 5, or 6.6. 6.6 is a very, very large z-score. So when we go to our table and we find our probability associated with 6.6, we're going to get 0.9999. But again, remember, this is the probability to the left of 6.6, and we want to find the probability of 6.6 or larger. So 1 minus 0.9999, so 0.0001, a very, very small probability that the mean IQ score of only 9 randomly selected people is